So last time lecture was devoted to solvable Lie algebras, and let us now talk about nilpotent Lie algebras. So let me first define what is the lower central series. So the lower central series of a Lie algebra G is a sequence of ideals of G like that. So G inside we have D with lower index 1, then D with lower index 2, G, and so on. And this D with lower index are defined recursively. So this one is D0, G, this one the same as we can write D, G, but also this is the same as D with upper index G, where upper index means it's a derived series. And we just write the following. DIG is the commutant of G with Di minus 1 G. So this is our definition, so we'll need this to say what is a nilpotent Lie algebra. So a Lie algebra G is called nilpotent if there exists some k, which is a non-negative integer, such that d I g is just 0 for so that I should say like this: dkg is just 0. Of course, dk plus 1 then is also 0, and so on. Okay. So this is the definition of nilpotent. And we have the following proposition, which is just similar to a proposition that we had for solvable Lie algebras. So proposition goes like this. Let G be a finite, again. So this might be redundant, but let me put this just to make sure that I'm safe. So last time this condition we figured was redundant, but I might be mistaken. So then the following is equivalent. G is nilpotent if and only if there exists a sequence of ideals of G such that so A0 is our G, but then inside A0, right, inside A0 we have A1, and then A2, and so on. And then I have AK, which is 0. And I have condition on this ideal such that AI with G is inside, it is inside AI, of course, but I need something stronger. It is inside AI plus 1. So proof is completely similar to what we had in solvable case. So just similar to solvable case. So in this direction, you just take AI to be dig, and you can check that this happens. Right. I will not. So this is just similar check to what we had. It's pretty easy. Let me not spend time on that. And in this direction, you just prove by induction on I again that d over ig is inside AI, and then of course then dk is 0. So details you can recover yourself. It's just similar to what we had. All right. So next I would like to state that nilpotency is stronger condition than solvability. So nilpotent implies solvable. Proposition. Any nilpotent Lie algebra is solvable. Proof. Again, some induction, I guess. So we prove by induction on I that d upper I G is inside d over IG. Okay, does everybody remember what is upper? So Santiago, you were not last time, so should I remind? Or at least define. So this is what's called derived series, and so derived series, it also defined recursively like this. So dig, upper I, is a commutant of di minus 1g and di minus 1g. So for lower center series, you have just g here. For upper, is just d's on both sides. And solvable means that this derived series establishes at 0 in the similar way as for nilpotent for lower central series. Okay. So this is a reminder. And then, so I would like to prove that. Well, of course, if I equals to 0, then both things are just g, and this is just obvious. And step of induction goes like this. So I take dig and just write down this di minus 1g di minus 1g, right? Some elementary. So this is inside d lower I minus 1g. This one inside lower di minus 1g. And but this thing inside g, of course, I don't even need that. So this is inside g di minus 1g, and this is by definition dig. And so step is proved and the proposition is proved. Okay. So last time we had very natural example of solvable Lie algebra, which are upper triangular matrices. There is similar natural example of nilpotent, which is strictly upper triangle matrices. But you can also take your flag to be not full in this case. So let me fix some complex, say, vector space, complex, finite dimensional, vector space, and a flag. So consider flag, which is a sequence of subspaces, right? So 0, v1, v2, v, say k, v case is v, okay? And then I would like to define the following Lie algebra, which is subalgebra of GLV, and it depends on flag as follows. So I take all x such that it moves everything from in Vi. So image of Vi lives inside Vi minus 1. Okay. And proposition is that n of f is nilpotent. And my flag can be any in this case, right? So you should really think about block upper triangular matrices, block strictly upper triangular matrices, okay? So, and full flag means that dimension of V2 is dimension of V1 plus 1, dimension of V3, dimension of V2 plus 1, and so on. So this is full, but in our case, F is not necessarily full. Well, this is kind of obvious because if you have something in strictly some subalgebra that lives inside strictly upper triangle, if you take commutators, this will be 0. Just some elementary manipulations with matrices, right? But we can make use of this proposition that was on this board, just a minute before. So we define subalgebras inside N of F, which we also had in last lecture. So these are X in G of V such that X Vi is inside Vi minus J. Right. Then A1 is then, of course, N itself. Right. And so these are actually ideals. So AIs are ideals. So we actually have this picture that was in this proposition. So A1 is N, and then I have ideal A2, A3, and so on. And VK, AK, right? So, of course, V with negative index, I think of it as 0. Right? So AK, I have only 0 transformation in AK. So this is N of F. And I would like to see that this condition that N of F with AI is inside AJ is inside AJ plus 1. Then I'm done by my proposition. But this is clear because A1 with AJ. So you take two matrices, right? One and compose them in two orders, right? So when you compose, you shift this index by 1 and then by j, right? So actually, when you apply any of terms in this commutator to Vi, you'll get Vi minus j plus 1, right? So this is actually inside aj plus 1. So therefore, N of F is nilpotent by proposition. By proposition we proved before. Right, next result that we need. So all this we will use one way or another next semester. We will study more systematically what's called semisimple algebras. I will define them today. So we're kind of preparing instruments for ourselves for the future. And okay, one thing that we'll use for sure is the following statement. All right, so G is solvable if and only if the derived algebra, so G is nilpotent. Proof. So if part, right? So if this is nilpotent, then G is solvable. So let's assume that G is nilpotent. Then, as we proved, G comma G is solvable. Moreover, G quotient by G by commutant is abelian, hence solvable. So we have quotient of G solvable, and ideal with quotient by is solvable. Therefore, by results of previous lecture, we know that G is solvable. Okay. So if part, only if part. So let us assume that G is solvable. So assume G is solvable. Then apply Li theorem to adjoint representation of G. To the adjoint representation. So there exists, so Li theorem says what? That if I have representation, there exists some basis such that all matrices corresponding to all elements of G under this representation are upper triangular. Okay, so adjoint representation means that as a vector space, I should take G itself. And so this basis given by Li theorem is the basis of G. So let x1, xn be the basis, or a basis, I should say, of G given by Li theorem. Which means that add x for any x in G is upper triangular in this basis, right? So I consider, so in other words, I can fix a flag, right, which is full flag, V n, right, n is the dimension of G here, where Vi is just span of x1, xi. And then let me consider B, which is our solvable Lie algebra given by this flag. So upper triangle. So what I'm saying is that really is that consider Lie algebra of upper triangle matrices in this basis, right? Then add G is inside B, right? So what I mean by that is that well, it's an image of adjoint representation, right? Which gives me some. So this is sub-algebra in GLG, right? And this is also sub-algebra in GLG. So this statement makes sense. Then I do the following. I consider add of the derived algebra. So since add is homomorphism, so this is just add G, add G inside this. So this is just because this is representation. This is a joint representation, so it respects bracket. So that's what this states. Then this is inside B, right? And so we should recall what we did last in last lecture. We had this B, right, and we had full flag, and we actually computed this commutator where it lives, right? It actually lives inside A1, right? This is what we proved actually last time, and A1 is exactly n of f with respect to this full flag. But n of f is nilpotent, right? So therefore, this thing is nilpotent, right? So n of f is nilpotent. So therefore, the image of the commutant is nilpotent. Right. So there exists some k, right, such that dk of add of g comma g, right, so dk of this thing, upper k, is it upper or lower? I think it's nilpotent, right? So I need lower index here, right? So for nilpotent, it means that a lower central series stabilizes at 0. So this is 0. On the other hand, again, I am using that add respects bracket, right? So therefore, add of dk of g, right, is 0, right? What I'm improving? So let's recall. So I am proving that this is nilpotent, right? So I assume that G is solvable. I'm proving that G comma G is nilpotent. All right. So I just need to, kind of expand in more details what this thing means. What this means, just to write this down explicitly, what is dk of G comma G? So I take first G comma G. Well, I can think of, so these are linear combination of commutators, right? So first I can take commutator of x2 with x1, so these are elements of G, right? And then I'm applying more commutators, so x3, x4, and so on, and all the way up to xk. Right? So this k is this k here. But then adjoint of it is that if I apply this thing and commute it with something, it's 0. Right? So let me commute it with something, say y. So this thing says that this is 0 for any y, x1, xk from G. right? But this just means that so let me see. So first of all, I took yes, I need actually my x1, xk to be from g, comma g. I can take this, right? Because this is my starting point, right? And then I start commuting again for so starting, you know, so this is my what elements of lower center series are. But then I commute with any element, so from G. So I can take y from any element of G here. In particular, I can take any element from here as well, right? So I'm not in wrong if I replace G with G comma G here. In any case. But again, then this means just that dk plus 1 of g is 0. So there exists some number, in our case it's k plus 1, such that lower center series of g comma g is 0. So it means that the commutant is nilpotent. Is nilpotent. And we are done. Okay. Any questions so far?
It's true in general that the Lie algebra is nilpotent even if the joint of it is nilpotent, right?
You mean that this is?
I mean the image of
Well, yeah. It's just, you know, writing down explicitly what it means.
Just write an exact sequence.
Uh,
Center into the algebra and then to the joint and use something like we proved with quotients and so on. And it will be a bit faster.
Yeah, I guess. Well, it's just, I mean, it's just a more explicit way to do that. Yeah, yeah. All right. So next thing that I would like to state is a theorem that actually is just pure linear algebra in a way. So we can ask ourselves natural question, right? So we had Li theorem for solvable Lie algebras, which states that, okay, we have representation, and this representation we have basis such that our elements that represent elements of Lie algebra are upper triangular. So nilpotent is associated with strictly upper triangular, in a way, matrices. So can we have a basis in any, say, finite dimensional representation such that we represent our nilpotent Lie algebra by strictly upper triangular matrices? So this is not true as it is, because, well, you can take abelian, for example, Lie algebra and you know, represented by, you know, scalar matrices, right? They commute, of course, scalar matrices. So which are not diagonal, upper triangular. But the following theorem is true. So if V is, it's not more or less about nilpotent Lie algebra, but I mean, it's related. So V finite dimensional vector space. And G is a Lie subalgebra of GLV, such that we have, it consists of nilpotent matrices in just usual way of nilpotency, right, a to the n is 0, so we just take a matrix and start multiplying it by itself. So if this is 0, so this is 0, I should say, so n can be different for different a, so I should state it more accurately, so such that for every a in G, there exists n such that a to the n is 0. Okay.
But since it's finite dimensional, we can just take the maximal value of n and like find the one for which every element to the nth power is 0.
Yeah, you can take the yeah, but at least one should exist. Yeah. No, it's not the whole theorem.
I know.
Yeah. Okay. So the thing is that there exists basis of V such that for every x in G, so such that every x in G are strictly upper triangle. Okay, so we are not going to prove it. I mean, so it is not hard to prove. It's just in the same fashion as proof of Lie theorem. And you know, we'll not learn anything from that proof. So again, you kind of need to start with finding just one vector, which is eigenvector for all of them of eigenvalue 0, and then prove by induction. But finding this vector is again kind of in the same fashion that we did it for a solvable case. Again, this is the proof that I know. You can read it in SER if you really want to. Maybe there are some better proofs, but this is how I know you can prove it. What is more important for us is the theorem that is corollary to this, which is called Engel theorem. And it says the following: a Lie algebra G is nilpotent if and only if for every x in G so add x, it is in G is nilpotent. So this guy is nilpotent in the sense of linear transformations of space G, right? So this element at x in some power is 0. Okay. So let's prove it. We just deduce it from this theorem that we had in here. First let us assume, so this is only if, I guess, right? So assume that G is nilpotent. So okay, only if part is obvious, and don't even need to write anything, right? Because add x is what? Okay, so we just need to look at it for a moment, and then it becomes obvious, right? So if I take nilpotent, it means that taking commutators at some point gives me 0. This is exactly what it's written. Add x, if I apply it, commutator with x, a bunch of times, it just will be 0. So that's what it means, that x is nilpotent. So only if part obvious. Okay, if part. So I need to take, so suppose that for every x and g, add x is nilpotent, right? So we actually have, it means, so we can apply the previous theorem, right? So we take g here, so in previous theorem, so apply previous theorem to, well, G, so I put quotation marks because I will have two G's in here, which makes no sense as it's written, but this G is from this theorem, right, and this G is from this theorem, right? So I'm just taking add G, right, and apply it, apply this theorem to that, right? Because if I take add G, right, then every element of add G has this property, right? So then there exists a basis of V, and V is G in our case. So then there exists basis of, so say x1, xn of G, such that add G is consists of strictly upper triangular matrices So let me just take GI to be, well, x1, xi. So span, linear span of first I vectors from this basis, right? So I have sequence of subspaces GI inside G, and I take add x, right? If I apply it to GI, then the result will be inside GI minus 1. Because my matrices are strictly upper triangular, right? So if I apply matrix, add x, right, this will give me vector which is spanned by x1, x2, and so on, xi minus 1. Okay, and then so therefore G. So this just means that G commutant with GI is inside GI minus 1. Which means in particular that these are ideals of G. And moreover, I have sequence of ideals such that if I commute with G, then I have result inside the smaller ideal, right? Remember we had this AIs. So AIs, they were enumerated in different way, right? The small ideal was I plus 1. So here it's I minus 1, right? So again, using the proposition about the criterion of nilpotency, that existence of these ideals. So we conclude that G is nilpotent. G is nilpotent. All right. So we proved Engel theorem. Sometimes people write Engel's theorem, but this doesn't sound good, at least for Russian ear. So, so I prefer just say Engel theorem. All right. So next thing that I would like to say is, okay, so now is the time to define what is semisimple algebra. Semisimple if it contains no non-zero solvable ideals. And let us right away define what it means to be simple. So G is called simple if it is not abelian and contains no and has no non-zero proper ideals. Okay, just looking at these terms, it's natural to ask if simple is semi-simple, right? Of course, it is. As it's written, it should be proved. So let's prove it. So, okay, proposition, it's not that hard. But later, we will learn that semi-simple is direct sum of simples. It's not that obvious from this, but it will be obvious once we prove complete reducibility of finite-dimensional representations of semisimple Lie algebras. Okay, so G proposition goes like this: G is simple implies G is semi-simple. Okay, so let G be simple. Suppose suppose I is non-zero solvable ideal. I is non-zero solvable ideal of G. Well, the only way this might be true is that I is G itself, right? Because G is simple, so it has no non-zero proper ideal. So the only way for I to be an ideal, it should be not proper. So it should coincide with G. So G is simple. So therefore G and I is the same. So therefore G is solvable right? So therefore, the commutant of G with itself is not G, right? And so it does not coincide with G. On the other hand, it cannot be 0 because so this is because G is solvable, and this is because G is not abelian. So we have an ideal, proper, not 0, which is contradiction to G being simple, right? Right. So G is non-zero, proper ideal. And this is contradiction to contradicts to G being simple. Okay, so we already saw some examples of semi-simple or on the seminar. I think somebody, Alexander, I think proved that SL2 is simple. Let us not. So this is some computation, but again, there are some criteria how to check which is semi-simple, for example, and then some additional work can be done to check that it is simple. But for SL2 and maybe even SLN, I think it can be done just in a straightforward way. So say SL2 is simple. Was it?
Only over complex numbers? As if
Yeah, I think.
fields, it will be
Yeah, I am saying over C, yes. Okay. So next, so we are moving towards Levi decomposition, which decomposes G into its maximal solvable ideal and semi-simple subalgebra. So for that, we first need to find this maximal solvable ideal. So proposition that we are going to prove is that for any G, there exists a maximal solvable ideal. And again, so let me assume that, so I'm thinking already about finite dimensional Lie algebras. I'm not, don't think. So okay, this is true for that. And my proof, I think, will require this to be true. Okay, so proof. So suppose that I have two ideals, solvable ideals of G. Then let me consider its sum. So I would like to see that sum is also solvable ideal. How do I do this? I take sum First of all, it's an exercise to check that this is an ideal. If it's not obvious, but I mean, this is just. So what is this? It's all elements, which is sum of elements from here and elements from here. And then, so I take this and quotient by, say, I1. And this is by isomorphism theorem, some number, I don't know, second. Okay, so it's I2 quotient by intersection. So I2 is solvable. So what do I need? Okay, I2 is solvable, quotient is solvable. So this is solvable. So quotient is solvable, and we factor by solvable ideal I1, right? So we factor by solvable, quotient solvable. So therefore, the algebra that we quotient is, ideal that we quotient is solvable. So therefore, I1 plus I2 is solvable. Okay. So let me take. So that's where I use finite dimensionality of G. So I take I to be a solvable ideal of G of maximal dimension. So suppose that I prime, right, is some other solvable ideal of G. Then I can consider I plus I prime is also solvable of dimension. So this is solvable by what we proved. And I plus I prime is inside. Contains I. Right? But since I is of maximal dimension, I plus I prime is just coincides with it, right? If it doesn't coincide with I, this is solvable by ideal of dimension greater than I, right? So I is of maximal dimension. Then, so therefore I plus I prime coincides with I. And this means that actually I prime is inside I. Right? So we actually found solvable ideal, right, such that any other solvable ideal is included inside, right? So of course it is maximal, so we proved proposition. We proved even more that, so maximal with respect to inclusion, so it's not included inside some other, but also every other solvable ideal is inside this one. and it is unique, also follows from maximality, right? So we proved that in finite dimensional G there exists an ideal, let's call it radical of G, and write like this, so called so okay, we will do it in the form of definition after that, such that, so it is such that it is solvable and any, so and for any solvable ideal I of G, we have I is inside radical of G. So definition so this, okay, I said it in words, so let me just put it on board to fix this terminology, is called the, and it's unique, the radical of G. Okay, so we have the following proposition, which says if I take radical and quotient by, then what is left is semisimple. So, well, it has actually two parts. So first is that this is semisimple, and the other part is that if B is solvable ideal such that quotient of G by B is semisimple, then B then what then B is radical of G. So proof. Consider an ideal. So yeah, so let me. So first I proved that G mod radical G is semisimple, right? So I need to choose. So semisimple means no non-zero solvable ideals, right? So suppose that I have one. So suppose I is solvable ideal in G mod radical of G. So let me denote somehow this projection from G to G mod radical of G. This is projection. And then let me take pre-image under this project. So I lift I to G. So this I denote as I tilde. So I would like to. So this is an ideal. It's easy to check, but so I would like to see that it is solvable ideal. So, well, of course, I tilde contains. So I tilde contains radical, right? In particular, because I has 0, right, and P inverse of 0 is radical. Okay, and then so therefore, well, radical is an ideal, and so I can take I tilde quotient by radical. And this will be just by definition I, right? It's just I apply projection pi. So it's just pi of I tilde, right? So this is pi of I tilde. So what do I mean? What do I have? So I have radical is solvable. I is solvable, right? I is solvable. So therefore, again, we use our usual technique. We say that I tilde is solvable. Very well. So since I tilde is solvable, it's inside radical, right? So we proved the other inclusion. So therefore, I tilde is radical, right? And therefore, I, which is I tilde by radical, is 0. So if I is solvable in here, then it's 0. So therefore, this thing is semisimple. G radical G is semisimple. All right. And the second part is the following. So suppose that I have such B. So it's solvable. It is solvable, therefore it is inside radical, right? So okay, this time let me take P to be maybe other letter, I don't know, the other P. So this one was pi, yeah, this one is P. So this is a projection from G to G by B. So I can apply P to radical of G, right? So this is radical over B, and it is solvable because it's a quotient of a solvable thing. All right, but it is inside semisimple thing, right? By conditions of 2, G over B is semisimple. And if it's solvable in semisimple, then it's just 0. So this is semisimple. So therefore, radical of G by V is 0. So it means what we need to prove, right? Radical just coincides with V. And we are done. So next statement that we would like to have about radical. So theorem. So let V be an irreducible complex representation of some Lie algebra G, then radical G acts on V by scalar operators and moreover if I consider an ideal here, which is G comma radical of G. So this also acts on V by scalar since it's inside, but this acts by 0 on V by 0. Okay, let's prove it. All right. So radical is solvable, and this is a representation of solvable Lie algebra. We can apply Lie, well, rather not Lie theorem, but the theorem about common eigenvector, which is kind of the same as Lie theorem, right? So G, radical G, is solvable. So therefore there exists a vector V inside V such that HV is lambda of HV. So this is some complex number depending on H, and this is H is an element of radical of G. So we can actually define the following subspace V lambda. So this is all vectors in V, right? Such that HW is lambda of HW. So this is eigenspace of radical with eigenvalue lambda, right? So this is for every H from radical G. And this lambda is the same as this lambda that appeared here. So I claim that V lambda is irreducible, is invariant, is a sub-representation of G. Then we'll conclude that So if we prove this claim, then V lambda is just V, right? And we prove this part. But this is just the computation that we will have in proving this claim. So, okay, let me take W from V lambda. I would like it to be not 0. And let me take X, an element of G. And let me take H, which is radical of G. Right, so I would like to, so what I need to prove? If I take X, W, and apply H to it, this is the same as multiplying by lambda of H, this thing, right? And then I'm done with this claim. Okay, so I just need to commute, right? So if I commute, I will have X, H, W plus the commutator W. Okay, this thing is lambda of H of W. And this, so this belongs, so AH is from radical. Radical is an ideal, so therefore when I commute, it's still in radical. So this is another element of H. So therefore, this is lambda of HX W. So the only thing that we need to prove is lambda of HX is 0. And then we're done with the whole theorem. All right. So I just denote WK to be XK W. Well, suppose suppose n is the smallest number such that W1 and so on, sorry, I need maybe start with W0, which is W itself, right? Wn are linearly independent. Okay. So then let me take W and span. So W is a span W0, Wn. Okay. So at least W is an invariant subspace of X, right? So therefore, right. So, yeah, I would like to take HX. So on the other hand, W is also is invariant subspace with respect to radical of G. It's just this computation again, right? So I take some x to some power W and commute, and what I will have is just W with lower index, right? Plus, so it just again expresses through WKs, right? If I take WK and apply some element from radical, right? So it's just just from commutation relations, right? In particular, so this is, so let me just state it. So this is invariant subspace for for radical of G. So this is also in radical of G. Okay, and then I can take this and compute its trace over W. Okay, so this is becomes some matrix if I apply it to W, and I can compute this trace over W. On one hand, since it is just trace of commutator is just 0, on the other hand, it is just n, right, times lambda of hx. Again, this is follows from the fact that and maybe I will write it here, that every h from radical is so I guess I need to write rho w of h is of the form it's just upper triangular matrix with lambda of h here, something here, and 0 here. Okay. So this is just you just take wk, right? Apply it. So because if you take wk, apply some h to it, so it will be lambda of h of wk plus wl with l less than k with some coefficients a, k, l. And this just follows like by induction from definition of wk's and commutations. Okay, so it's just something similar to Li theorem, that how we proved Li theorem. We also had such thing. So therefore, on one hand, this trace is 0. On the other hand, it is so if I compute, right, trace of such matrix, so it will be just n. Well, I guess I need to take n plus 1 here, because really I have dimension of W is n plus 1, as I put it here, right? So I just sum up diagonal entries here. Instead of h, I have h and x, a commutator of h and x here. So from here, I see that lambda of h and x is 0. So therefore, this is 0, right? So h acting on xw, right, is x times lambda of hw, right? So it means that, okay, let me finish writing just to make sure that we did everything. So what we get? We get that h of xw is lambda of h xw. So if I take w in v lambda, then xw is also in V lambda by definition. Right? So xw also in V lambda. So V lambda is sub-representation. And we proved this claim. So claim is proved. But this means that V lambda is V, right? Because V is a reducible representation. And if I have some sub-representation, it should coincide with V, right? So it means that radical acts by scalar operators on V. So it acts by scalar operators on V lambda, but V lambda coincides with V. Since V is irreducible. And moreover, this number, right, this scalar operator, is just multiplication by some number, this number, right? If I compute some element from radical, right, with some element from G, commutator, then the corresponding number is 0. And that's the second part of the theorem. So we proved the theorem. So again, radical on any reducible representation acts by multiplication by numbers, and this number is 0 for every element from such thing. Right. All right. So next logical step is to say, okay, if I have an algebra where such thing is not 0, then studying finite dimensional representations, irreducible representations, I lose a lot of information because this thing acts by 0, right? So this is in a sense situation that I don't want. And so if this thing is 0, then the corresponding algebra is called reductive. So definition. G is called reductive if G commutant with radical of G is 0. Or what is the same, it is just the same, it's easy to see that the center of G, what is the center? So let us recall. It is all x in G such that it commutes with everybody, right? So then this is the same as radical. Why this is this equivalent? So this and this. Okay, let's see. Center is a commutative ideal. It's a abelian ideal. So therefore, it's solvable. So therefore, it's inside radical, right? In any case. All right. On the other hand, this condition says that radical commutes with everything. So it's inside center. So therefore, these two things are the same. So reductive means that radical is the same as center or this condition, so they are equivalent. All right. And finally, so we will conclude this semester by two strong statements, which we are not going to prove, at least today. So the first statement but these are very important results in structured theory of Lie algebras. For a reductive G, we have the following decomposition. G decomposes as follows. Its center of G direct sum with something which is semisimple. So where GSS is a semisimple ideal. So let me stress that this is an ideal here, meaning that this is really direct sum of Lie algebras. So things from here and from here do not commute. In any case, if you found a subalgebra in here, right, semisimple, such that this happens, right, as it's just direct sum of vector spaces, then since it is a center, it commutes with GSS, and this becomes direct sum of Lie algebras in any case. All right, but this theorem is a consequence of another theorem, which is called Levi decomposition. So theorem 2. Levi decomposition. It says for any G you have the following. G can be decomposed into its radical and G and some subalgebra. The only thing that maybe I can stress it that it is not direct sum of Lie algebras, but by putting such symbol, whatever, it means that it is semi-direct sum. Yeah, I think we know from seminars at least what is semi-direct sum. But really what it is that we have, so where GSS is semisimple Lie subalgebra. So in other words, you can put just usual plus here, but think of it as a just direct sum of two vector spaces. So this guy is an ideal inside G, and this is subalgebra inside G, semisimple subalgebra. But this one is not an ideal in the sense that something from here commuting with something from here can give you something non-zero. All right? Unlike in here. This one is, well, it can be proved in, I think, half a seminar, or maybe more than half. So I have So you can go to Sarah's book, for example, and read a proof there. Or I have like a list of problems that can lead you to. So this one is not so hard to prove. And this is just consequence of this. Also, we will prove, this might be, so this follows also from some theory that we will study in the future. And let me give one last comment before we all go, not to holiday, but to seminars. But okay, so that Levi decomposition is powerful for number of reasons, but in particular we had Edo theorem, and to prove Edo theorem, you might use that you have Levi decomposition. That's one way to do it. Okay, so for semi-simple, so Edo theorem says what? That there is a faithful representation, faithful finite-dimensional representation of your finite-dimensional algebra. So for this one, it's easy to construct faithful representation because it does not have center. So therefore, a joint representation is faithful. And for this part, well, to extend it to this part, you need something more. Okay, so let me conclude our lectures for this year. Now, thank you.